So could you tell us about who you are?
Sure. My name's Josh Rovey, and I'm a professor of aerospace engineering at the University of Illinois in Urbana-Champaign. And so I not only teach classes in aerospace engineering, in particular space propulsion, but I also direct the Electric Space Propulsion Laboratory at the University of Illinois.
Mhm. So why did you want to become an aerospace engineer?
Well, I became interested in really, I'd say, space at a young age. I was interested in rocketry, and probably from the first time I built one of those small Estes model rockets, that really piqued my interest and drove me to attend a aerospace summer camp, actually at the U of I when I was in high school, and that just further increased my interest and drove me to pursue aerospace engineering in college as a degree, and sort of that led to another stepping stone, and all of those have now led to the place where I'm at right now. And so I think it was just sort of an innate interest of mine was in space, everything space, and so my path has been focused on that throughout my career.
Mhm. What are some of the things that you're researching in space propulsion?
Right, so that's my background expertise is space propulsion, and in particular electric space propulsion. And so what that means is on a spacecraft or on a satellite, we use the onboard electrical power. So the electrical energy gathered by the solar panels or maybe from batteries on board the spacecraft. We use that electrical energy to power the propulsion system. And so things we're working on in this area right now, we're working on electric propulsion for small satellites, or what are called cube satellites or nano satellites.
Mhm.
And you have to do things differently whenever you're talking about such a small platform like a small satellite or nano satellite. You have to think about doing propulsion differently, because the propulsion system has to also be small to fit on that small satellite. Not just physically small, but the mass of the propulsion system also has to be small. And so we're exploring we're exploring a type of space propulsion called electrosprays, where we electrically accelerate a charged fluid. And so it's much like it's sort of like an inkjet printer, where you have a jet, a spray of liquid that you'd be using to print on paper, except for us, we're spraying that jet of liquid out into space to provide a propulsive force that will move the satellite around, propel the satellite, move the satellite into a new orbit. And one of the things that's really important there is how that jet of liquid, how that plume or that spray of liquid, how that interacts with other materials and surfaces that are on the satellite. You don't want that jet of liquid to coat your solar panels or cover up the mirrors and optics that might be on your satellite. And so we have to understand how these jets of liquid in an electrospray, how they interact with materials and surfaces that are relevant to satellites and spacecraft. And so that's one of the main research activities in my group right now in space propulsion.
Mhm. What are some electrical propulsion examples other than electrically powered propellers that you can tell us?
Yeah, this is a great question, and it's a great way for me to kind of contrast what I do with what's been an emerging but is now a somewhat established area: electric aviation, electric aircraft propulsion.
Mhm.
Right. So my area of research is focused on electric space propulsion. So here we're talking about satellites, spacecraft, again, that use the electric energy, the batteries, the solar panels of the satellite to provide the energy to do propulsion. And that, again, that's to be contrasted with electrically powered aircraft. And again, that's been an emerging and growing area, how to use electrical energy to power and propel aircraft. But here my focus has been on spacecraft and propelling spacecraft using electrical energy. And so examples of electric propulsion, so I already mentioned the electro spray, where we have sort of a jet of liquid that's being expelled, and that jet of liquid provides the exchange of momentum, the force that's going to be used to move the satellite around, change its orbit, move it to a different orbit. But there's other types of electric propulsion. In fact, there's other types of electric space propulsion that are really dominant in space right now. And these are types of propulsion called ion thrusters and Hall thrusters. These are ion engines or plasma thrusters you might have heard of. I mean, a great way to think about it is to imagine like a Star Wars TIE fighter, right? TIE stands for twin ion engine, right? So in Star Wars, TIE fighters are propelled by ion engines. But that's actually not a futuristic technology. That's a technology that exists here today. And the use of electric propulsion in space has grown and expanded considerably over the past few years, really over the past decade in particular, such that now, there are hundreds of satellites in space today using ion engines and plasma thrusters on board. So this always used to be the technology of the future, but really the future has arrived, and there are hundreds of satellites using ion engines and plasma thrusters on board today.
Mm-hmm. And can you explain your work in plasma dynamics?
Yeah, one of the things we're doing in plasma dynamics, and the reason that's important, is because of the types of propulsion I just mentioned, ion engines and plasma thrusters. These types of electric propulsion, electric space propulsion, they rely on a plasma as the working fluid. And what that means is these rocket engines, these satellite rocket engines, they create and then expel plasma at very high speeds. And so to understand how the rocket engine works, how this electric rocket engine works, you have to understand how the plasma behaves, what its plasma dynamics are. And one of the things we're working on right now in understanding that plasma behavior is really understanding how the plasma behavior changes when you go from testing the plasma or testing the rocket engine on the ground, right? We have to test it on the ground and make sure it works before we fly it in space. And what we find is that the plasma behavior, the plasma dynamics change between the ground test versus when that electric rocket engine gets into space and you make the plasma, it behaves differently there. And so we call that a facility effect. The difference is because of the facility, like the ground-based test chamber that you have to test the rocket engine inside of. That facility perturbs and modifies the plasma such that it doesn't behave exactly the same way as it would if it were in the actual space environment on a satellite, flying around in space. And really there's sort of two main areas or two main issues. One is when we try to predict the performance, how much thrust, how much force this rocket engine would produce, it's actually a bit larger on the ground than it is when it gets into space. And so what we're working on is developing models, developing an understanding why is the thrust that we measure larger on the ground versus when we get into space, and then how do we correct for that? How do we modify that ground-based measurement to do a better job of predicting what will happen in space? The other question has to do with lifetime of the thruster. How long will that thruster, that rocket engine, how long will it last? Meaning how many years can I operate it for before it'll be at its end of life? And again, that prediction, that measurement is clouded by the ground-based facility that we tested in. And so that's one of the kind of the main areas of research going on right now, is trying to understand how those plasma dynamics change from the ground-based testing to what's actually going to happen in space, and then being able to correct or account for those changes such that we can take the ground-based measurements and accurately predict what will happen when that electric rocket engine gets in space.
Mhm. So what are nanosatellites?
Yeah, so nanosatellites, kind of like what it sounds like. They're small. Nano is small. Satellites are spacecraft, and so these are small spacecraft. And by small, I don't mean nanos. We're not talking about nanometer, super duper small satellite. By nanoscale, what we mean is a satellite that's maybe on the order of centimeters or a few tens of centimeters in scale. It's something on the order of this kind of size. Other names for these nanosatellites you'll hear are cube satellites, for instance, and they are pretty much like what they sound like. It's a cube, a 10 by 10 by 10 centimeter cube. That's a 1U cube satellite. And then you can increase the size of the satellite, provide it more functionality, more capability, by strapping multiple cubes together to have 3 cubes, or a 2 by 3 array of cubes, have 6 of them or 12 of them. And so it's a way of creating spacecraft that's in a very modular type approach.
So can you explain some of the future space systems that you are currently working on?
Yeah, one particular future space system I'm particularly excited about is what we call multi-mode propulsion. So again, my background is in propulsion for satellites and spacecraft, and the idea of multi-mode propulsion is really to get the best of both worlds. So in space propulsion, rocket engines that we put on satellites, put on spacecraft, there's 2 main types. One is the electric propulsion that I've talked about, ion engines, Hall thrusters, these electrosprays. These are all electric propulsion rocket engines for satellites. The other type is the type that you've probably seen a lot before in launch videos, right? SpaceX, or previously space shuttle type launches. These are chemical rocket engines where you see the fire and the smoke that's produced. And so you have electric propulsion on one end, and on the other end you have chemical propulsion. And the difference is that chemical propulsion provides a lot of thrust, a lot of acceleration. If you need to get where you want to go quickly, you got to use chemical propulsion to give you a big push, strong push to get there. But electric propulsion provides a benefit in that it's very fuel efficient. It's slow, it doesn't provide a lot of thrust, but a lot of force, but it's very fuel efficient. The force it does produce is very fuel efficient. And you can kind of think of it as, a chemical rocket is sort of like your Ford Mustang, right? You pull up to the line and the light turns green and you hit the accelerator, and boy, you get off the line quickly with lots of acceleration, lots of force. Whereas electric propulsion is more like a Prius or like a Chevy Volt, electric automobile, where you're not going to accelerate off the line very quickly. You're going to slowly speed up, but you will do that, and you can travel very long distances because of it's very fuel efficient. You're using your fuel very fuel efficiently. And so what we're working on, the future space system we're working on, is what I call multi-mode propulsion. And it's really to try and combine both of these together to get the best benefits from both of them, and combine them together into one system, such that if you need to do a very fast, quick, timely maneuver with a big force, you've got chemical propulsion on board and available to you. Or instead, you want to do a very slow but fuel efficient maneuver. You want to get where you're going without having to use very much fuel, very much propellant to do it. You've got an electric propulsion system on board. And so multi-mode propulsion is trying to marry these two together into a common system with shared propellant, shared fuel between the chemical and electric propulsion modes. And that significantly enhances the capability, the flexibility of a satellite, and enables it to do a very wide range of missions and mission maneuvers, because you've got the best of both worlds on board that spacecraft, both chemical and electric propulsion on the spacecraft.
Mhm. So what has been your toughest accomplishment so far?
I don't know if I'd say, toughest accomplishment. I would kind of prefer to say, maybe some of my, proudest moments, I would say. I think that's really seeing my students grow, and both technically and professionally throughout their time as a student. And that could be an undergraduate student or graduate students who are doing research in my lab. Seeing their progress, seeing their growth over the course of their time in in my laboratory, leading to their graduation, and then seeing them graduate and go on to become professional engineers, researchers in academia, in government labs, or in industry. I think, so I wouldn't say it's necessarily a tough accomplishment, but I think it's sort of the most rewarding part. It's an accomplishment, certainly for them, but also for me to a certain extent. And I think that's what's probably my proudest accomplishment is the students that have graduated and gone on to do just amazing, phenomenal things while they were my student, but then even post-graduation, their accomplishments.
Mhm. Is there a big milestone that you're looking forward to in your research?
Well, I think something that I'm looking forward to, over the horizon, is our multi-mode research. This idea of combining together chemical propulsion for spacecraft with electric propulsion for spacecraft, combining that together into multi-mode propulsion. I'm looking forward to flying the multi-mode propulsion approach that we are working on in my lab right now. We're not there yet, but we're on track. We're making progress, and so I think that's something I look forward to, over the horizon.
Mhm. And lastly, to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
Yeah, great question. I think maybe starting off a little bit more broadly than that, not just aerospace engineering,
Mhm.
but just advice in general, I think is to, at this stage, to really have as many experiences as you possibly can. Don't be afraid to try new things. And really, that allows you to learn more about yourself and what you're interested in, what you're passionate about. And then I think, when you discover that, or you think you discover that, pursuing that, and that was sort of my approach, or my path to where I'm at, is I was passionate and interested in rockets and space, and that led to other opportunities, other activities that I pursued. And so I would say, don't be afraid to try new things, try lots of different things, and really try to figure out what you're passionate about, what you're really interested in. And then I think the second key, then once you figure that out, though, I think the second key is and this was advice given to me by a senior colleague a number of years ago on how he had been so successful, is to be tenacious. It's tenacity. It's, being diligent, sticking with it, because I think you will find that there are going to be people tell you no at some point, along your journey. Someone's going to tell you no, no, that can't be done. No, you can't do that. And I think you just have to stick with it and just keep going. When everybody else has gone home, you're still at it. You're still going at it 100%, still giving it everything you've got, being tenacious like that. And so I think if you're tenacious like that, and it's focused on something you are passionate about and really interested in, I think success just comes naturally when you have those two things combined together.
Mhm. Well, thank you for joining me, and thank you for letting me interview you. That was nice.
Yep, great to meet you, and thanks for the
Mhm.
opportunity.
All right.
Good luck.
Have a great rest of your day.
Thanks.